Get started today. Reminder that we have our second midterm on Tuesday and in lab on Wednesday, the coding portion of that exam. I have posted the 3 example coding problems from spring 2015 midterm to the Code Assessor website, so you should be able to actually practice those problems. The solutions are on the CS140 website. If you go to the exams link, then you can find the actual answers. So go to the exams link and you go to midterm 2 coding. That will give you the worksheet that you can work from for those questions. And then the solutions allows you to look at the solutions. So at the very bottom, it has the solutions for the coding part. Remember, you have a 1-page cheat sheet for the lab, but not for the exam on Tuesday. Not going to go through all the details. If you weren't here on Tuesday, go back and look at the video lecture for Tuesday. I have all the details about the exam there. Any questions about material or anything? Yes.
I have a question about the lab. So when you delete a pointer.
Okay, just a sec. I'll take your question about the lab. Just anything about the exam first. Anything about? Okay, proceed with your question then.
So when you delete a pointer that points to a user, right? And in the user there's a set that has all the numbers. And when you delete the pointer, will the set call the
destructor? Yes.
So that will delete all the
yes. Good question. So the question was, for Lab 7, you have a pointer. So let's say you have a pointer. Whoops. Well, just a second. Let's do it this way. Let's say you have a user star pointer, so U. So U points to a record, and it has some stuff, and one of the things it has is the phone number set. Okay, so that's a set, which I'm just representing this way. And if you look at that definition in Lab 7 for phone number, you'll see that this is not a pointer. This is an actual object. Okay, so the question is, if I say delete U, that's going to delete this object right here. The question is, does it also cause the set to be deleted? And the answer is yes, because it is an actual object associated with that's nested inside of this object. If it were instead a pointer, then the answer would be no. So when you delete an object, it will not chase the pointers. But any object that's embedded in it will be, or nested in it, will be deleted automatically. Okay? It's just like a function. So if you have a function, int foo, and you have 2 variables, you have, say, stack A, and you have stack star B equals new stack. Okay, when this function exits, this object will be reclaimed and its destructor will be called. This object will not be reclaimed because while it will reclaim the 4 bytes associated with the pointer, it will not reclaim, it will not chase the pointer to find the object to which it points. And in this case, you would end up with a memory leak because B was the only pointer to this object, and so this object would no longer be accessible and you'd have a memory leak. Okay, so bottom line is, when a function returns or when you delete an object, any what we call stack allocated objects are automatically deleted, but anything that's pointed to by a pointer is not. And you have to do it manually. Okay? Does that make sense? Okay. Other questions? Okay. In that case, we have linked structures to go over today. And so before I get into things, just to note that after our midterm on Tuesday, week from today we start recursion, and I'll be honest, that is the hardest topic we cover this semester, harder even than pointers. So please be sure to read the book before you come and do the exercises before you come on Thursday, or otherwise you're likely to be just completely lost. Okay? Recursion takes a while to get used to, and we'll be spending basically the rest of the semester on recursion after the midterm. Today, however, we'll be finishing up linked data structures, and we're going to be talking about the implementation of queues and lists today. So just quickly going to review what we did with stacks. So if you remember, a stack has two operations, push and pop. Push adds a new item. Conceptually, a stack looks like this. And you add new items to the top of the stack via an operation called push. And you remove items from the top of the stack and return the top item via an operation called pop. And the way we implemented the stack was through a list, and it was a linked list, so each item in the list had a next pointer that pointed to the next item in the list. We saw this particular constant null, which indicates that the pointer points to nothing. That's the way we know we've reached the end of the list. And then we have a pointer top that pointed to the first element of the list. We also covered the idea of the abstract data types. So this class stack is an abstract data type, and also that it's a container because it contains the implementation for a stack. The actual implementation is hidden from view so that we can change that implementation. In fact, I told you that the most efficient implementation for a stack is not a list, but is actually what? A vector. So it might be that I go and implement it as a list. I'm all proud. I go to my boss, and my boss says, that's not the best way to do it, Brad. You need to use a vector. So I complain to my boss, say, but I already have 5 people in the company using my code. The boss says, well, did you make everything, your implementation protected? I say, yes. He says, great, because all you have to do is change the protected implementation. As long as you don't change the public API, no one will know the difference. So that's why we protect the implementation. So this is a container object, and we access the various, we access the data via the public methods. And we went over those public methods. I will not be going over those today. Assume you got them. Instead, we're going to push on into queues. So a queue, if you remember, is a stack is what is called a LIFO data structure. So a stack is often called a LIFO queue, where LIFO stands for last in, first out. So in a stack, whatever was the last element inserted, when you do a pop, it becomes the first item returned. Okay? Now, we all are familiar with waiting in line, and we would do a slow burn if lines at the grocery store or at the bank were treated as LIFO lines. Unless, of course, we were the last person there in a long line and no one got there after us, in which case we'd be thrilled. But a queue, when it's not modified with anything, is typically called a FIFO queue. And it's the one that we're more familiar with, first in, first out. So basically what happens in a queue, conceptually, again, it looks like this. But new items come in at the back. And items are removed from the front. Okay, now the data structure we talked about a couple weeks ago was called a DQ for double-ended queue. And that was because you could add items at either the front or the back. And you could remove items from either the front or the back. So that's a doubly ended queue, but that's not what we're talking about today. Today, we're talking about a normal queue where the items go in at the back and they are removed at the front. Okay? So again, it turns out that the most efficient implementation of this type of queue is with a vector. It's more tricky than it is with a stack, but we won't worry about the vector implementation. Again, it gives us a nice way to talk about queues. And you can see the operations. Empty is the same as before. Push now adds items to the back, same as before, but pop removes items from the front. And we have a new method size that returns the number of elements in the queue. So the way we're going to organize the, we're going to keep 2 pointers now in our queue. We're going to keep 1 pointer to the front of the queue and a second pointer called last that's pointing to the last item in the queue. Can anyone tell me why we now need 2 pointers? First of all, someone tell me what's going to be the purpose of the first pointer. What operation needs to use first? Yes? The remove operation. The pop operation needs to use first. What operation needs to use last? Push, the operation that adds a new item to the queue. And then we also are keeping track of the size. We could dynamically compute the size by traversing the list and simply counting the number of nodes in the list, but that's inefficient because it's an order n operation. So we actually keep that piece of information, and we need to make sure that when we do our pushes and our pops that we update this size variable. Okay, so before we go into the code, I'm actually going to illustrate what happens when we do a push. So if we do a push, let's say that we are adding, what's his example? We're going to add oh, he's deleting first. I want to push first. Okay, so we're going to add now. Very good. Okay, so let's say we want to add now to this list. So the first thing we need to do, we need to create a new node. Okay. Initially, it's going to look like that, so we'll have a pointer to it called new node. Okay, so step 1, we create a new node. Okay, then we need to make new node point to what? Anything? What do we make new node point to? Okay, might seem like we're going to make new node point to last, but in fact, it's the end of the list. Okay, so actually we make it point to null, because it's going to be the new last item on the list. Now we need to make the previous last, whatever this thing is, we need to make it point to new node. Okay, so 3, make the last node point to new node. And what's the final thing we have to do? There's one last final step. Actually, there's 2 last final steps. There's 2 more things we need to do. We need to make last, we need to redirect it so it points to new node. And the last thing we need to do may be easy to forget. We need to increment size. So those 5 operations. Questions about that? Does this make sense? Okay, so we're going to go and have a look at our push code. So here's push. So right here is where we do step 1. We create the new queue node. So if we look at a queue node, it has a first and last pointer and a size. So we first create the queue node and make its S field be equal to whatever string is passed in. Then this is operation 2, where I made the new node point to null. Okay, now we are doing a little more complicated operation. We'll talk about this, but operation 3 is right here, make last point to new node. Okay, and then, I'm sorry, that's not operation 3, that's operation 4. This is operation 4 and that's operation 5. Operation 3 is a little more complicated. So I said make the last node point to new node. Okay, that worked fine, okay, when we had items on our list. So we need it, see, let's do it over here. Here was our list, and we simply made the last item point to new node. But what happens if, in fact, currently the size of the queue is null and first and last actually point to nothing? Okay, in that case, we can't make last node point to new node because there is no last node. In fact, if we just go ahead and try to say last pointer equals new node, we will get a sig fault. The reason we'll get a seg fault is because last is null. And if you try to dereference or go to the memory location of a null pointer, you'll get a seg fault. So we have to handle the special case where last is equal to null. Okay, if that's the case, we actually know that the list is empty. Another way we could have written this that might have been actually a little clearer is we could have said if size is equal to 0. Okay, because if size is 0, last is null. So if the size is 0, actually we need to set first to point to that new node as well as last. And otherwise, if it's not empty, if there is already a node in the queue, then we simply make that last node point to new node. So is that clear what I did there with that if statement? There was a boundary case. We had to handle the case where the list was empty and had no node. So 3 was a little more complicated because I needed to handle the boundary case. We good with that? Okay. So that's how we add to the end of the list. Now, we want to delete something from the list. So let's say that we again have this queue. We want to now delete the first element using pop. Okay? Well, so it's clear that we want to delete the first node. And 2, we're going to need to update first. So we need to make first point to the second node in the list. And we need to return the value of the first node. And as with a stack, we can't execute operation 1 first. Because if we do, we lose all the information associated with that node, including the pointer to the second node in the list. Notice that the first node is the only pointer we have to the second node in the list. So if we delete the first node immediately, we'll lose the pointer to the second node. We'll have no way of accessing it. And we'll also have no way of accessing the value of the first node in the list. So in fact, this operation needs to be performed last or near the last. Okay? Well, as with so if we move it down here, so if we reorder and make this be 1 and this be 2, and now we make 3 be delete the first node, doesn't quite work either. Can someone tell me why that doesn't quite work? Because in step 2, I returned the value and terminated my function. So that's no good either. You feel like, wow, I have a chicken and egg problem. I can't seem to reorder these operations in any way that makes sense. But what if we just save the value of the first node in the list, and as operation 4, we return the saved value? Now we have a working algorithm. Okay, so we got rid of the original step 1. Okay. And hopefully you'll agree that this is a functioning algorithm that we can implement. Okay. So, questions about it? Okay, so let's go ahead and do that. So again, there is a boundary case, which is we can't return something from an empty queue. So the first thing we do is check the size. And if there's an error, we print an error message and exit. Okay, we actually, in this case, did operation 2 first. That's okay. Operations 1 and 2 were interchangeable. And we actually needed to, so here, we are making first point to the second node in the list. But when we do that, when we make first point to the second node, if I go back up here for a second, if I simply make first point to the second node, then I lose the only pointer I had to the first node. So before I make first point to the second node, I need to save the pointer to the first node. And that's what I'm doing right here is I'm saves a pointer to the first node. Okay, now after I have saved the value of the first node and update it first to point to the second node, I can go ahead and delete the first node. Now there's a couple things that I did not put in there. It's easy to overlook. 3A was I really needed to decrement the size. And the other situation I had to do is I had to account for a list that had only one element. Okay. So if, as a result of deleting or popping this element, my list becomes empty, I have to update last to be equal to null, and that's what 3b is doing. It's saying if first is now equal to null. In other words, if the size of my list, again, it might have been clearer here to have written if size is equal to 0, but I would have to first, this is a tricky thing. Notice how if I'm going to say if size is equal to 0, then this statement would have to be moved up. Right? So order of operations can be very important. Okay, in this case, he simply said if first is null, because now if first is equal to null, it means our new list is empty, and that means we must also set last to be equal to null. Okay, and here was operation 3a, and operation 4 was to return the value. So just because I have an initial algorithm doesn't necessarily mean it's complete. Sometimes in testing you'll figure out you've overlooked something. And that's why rigorous testing is also necessary. You have to think about what are your boundary cases. And when you're writing code, it helps to think about what are my boundary cases. And it certainly helps to rigorously test your code, not just try it on a couple examples, but try to think of multiple examples and stress test it in effect. So questions here about push or pop? Yes, Charles.
So if we implement the queue using a vector, why do we even have to go through the process of using pointers and stuff? If with a vector we can just access.
Okay, so Charles has a good question. He said, if we were to implement the queue using a vector, why would we have to use pointers? And the answer is we would not. That's why vectors are more efficient. Okay, although a naive implementation of vectors would not be more efficient, because if we did it, say this was our vector and we had like 4, 8, 2, 1, 7, 6, and we did a pop and remove 4, if we do it naively and move 8 here and 2 here and 1 here, that's actually an order n operation. Okay, so that's actually a very inefficient implementation of pop. Whereas right now, we have an order 1 implementation. It's constant time. However, and it's kind of too complicated for this particular course, there are more efficient ways that you can do this. One way would be to actually just increment first so that it's equal now to 1, and this element is considered right. But also, you end up, and this is where it gets more complicated, at some point you reuse these things by wrapping last around so that it points to the beginning, and that's where it gets more complicated. I don't want to get into it. Okay, so you have to do some more complicated processing if you use a vector with a queue to ensure that it stays as order 1 operations. Okay. Whereas with a list, at least we're guaranteed it's a constant time operation. Yes?
So for queues, like every node is pointing to another node behind it.
Yes.
But theoretically, you can implement it the other way. Like
Sure.
You can have every node point to the node in front.
Yes, you could do it either way. In that case, you'd simply reverse the meaning of first and last. So if you'd have to reverse some other meanings too in doing that. But yes, you could reverse the order of the pointers, but you'd have to change some of the code too. Other questions? Okay. So let's then move on to the FOON doubly linked list. So what you've seen thus far is a singly linked list. You can only easily move forward in the list. Okay, so if I'm here at this node, I can't move backwards. Okay, I don't have a pointer from 6 to him. I don't know what precedes me in the list. Well, that defeats reverse iteration for one thing, right? Because you can't go backwards if you don't know what your previous node is. Also, think about what if I wanted to insert something. What if I wanted insert before? And let's say I want to insert now before 6. So let's say I want to be able to do that operation. Okay, and in fact, I know it's now. In fact, this would be a pointer. So let's say that this isn't really 6. This is actually a pointer to 6. Well, I can't actually implement the insert before operation because now needs to go right here. And if I insert now there, it's easy enough to make its next pointer point to 6. But what else must I do in order to insert now into this list? I need to make him point to now, and that doesn't work so well because I have no way to get to him. That's not exactly true. I could start at the beginning of the list right here and do a linear traversal through it, but that would turn it into an order n operation. And we don't like order n operations if we can avoid them. So the solution is a pretty simple one, which is we're going to add another pointer, which in effect is a back pointer, or a previous pointer. So every item is actually, or every list element is actually going to point back to the item in front of it. So we're going to point both ways, both to the item in front and to the item in back. And that's going to make it a lot easier to insert items into the middle of the list. Plus, we'll be able to move backwards through the list using a reverse iterator. And you'll recall that I told you the way that linked lists were implemented was with Sentinel nodes. So you might have give him 6, but we also had these strange beasts that were Sentinel nodes. Okay, and there's a reason for this. So you may have noticed if you read the book's description of doubly linked lists that their code was complicated by the fact that they had to consider boundary cases. So actually, let's just take a quick look at the book. And we'll take a moment for that animation to load. Okay, so here was the book's implementation of a doubly linked list. So they had 2 pointers, one to the head and one to the tail. And there's no Sentinel node here. Okay, every node is actually containing a data value. So you'll see that they have to consider 3 cases in their insert. So case 1, they're saying, is the list empty? Okay, case 2, they're asking, are we inserting after the tail? Meaning, are we inserting at the end of the list? And the third case is anything else. But they're having to consider 2 boundary cases that are complicating their code. Okay, and if we now go and look at their delete, okay, we see that there's also a whole bunch of cases. So if successor node is not 0, so they are here is their list, and let's say that they are right here, this is current node. Then they create 2 more pointers, successor node and predecessor node, which are on either side of current node. And the idea is that you're going to have to, if you're removing current node, you need to make predecessor node point to successor node, and you need to make successor node point to predecessor node. So that's why they're keeping track of the predecessor node and the successor node. But there's issues. Okay, it's fine if current node is in the middle of the list and there's a predecessor node and a successor node. But what if we are removing from the front of the list and there is no predecessor node? What if we're removing from the end of the list and there is no successor node? We again are having to worry about boundary cases that are complicating our code. And in general, boundary cases increase the opportunity for errors. Okay? So, the solution, that's a very elegant one, to making the code simpler is to use Sentinel nodes. Okay? So they may initially seem to complicate things, but they actually make our life a lot easier. So we have our Sentinel node, and then there's a second thing we're going to do to make life simpler. And that is we're going to create what is called a circular list. So what that means is that the last item in the list, rather than having its f-link point to null, we're going to actually make it point back to the first item in the list. Actually, that is wrong. That is correct, because this is the Sentinel node. Sorry. This right here is our Sentinel node. Okay? So it has no value. This one has no value. You see it's an empty string. So this is our Sentinel node. So we have the last item in the list points back to our Sentinel node. And you can see also the first item points back to the Sentinel node. So the last item is pointing back to the Sentinel node. So we have a circular list. Okay, now that adds some nice things. First of all, we no longer need first and last pointers. Okay, and you might think, oh, why is that? Well, because the Sentinel node also points back to the last item. So its B-link for the Sentinel node actually points back to the last item. So in fact, the Sentinel node has a nice feature to it. Its F-link, which is its forward link, points to first node, and its B-link points to the last node. So we don't need to keep first and last pointers anymore because we have a pointer to the Sentinel node. And the Sentinel nodes, F-link and B-link, give us our first and last. So that's a nice feature. Okay. Now, one thing that often troubles students, though, and actually I had someone ask me about this in office hours yesterday, is if I have a circular list, then how can I stop my list traversal? Okay, because if I'm traversing the list, it's going to be something like for some list pointer. So I can kind of say for pointer equals Sentinel F-link, because that's going to give me the first node, because the F-link points to the first node. And I'm going to keep traversing by saying pointer equals pointer F-link. But the question is, what's my stopping condition? When do I stop? Okay, it was easy when the last item in the list pointed to null, because then it used to be that I kept going while my pointer was not equal to null. But that's no longer true. We don't have a null pointer. So when should we stop our iteration? Yes.
Go all the way around and hit the Sentinel.
Very good. So when I come all the way around and I reach 6, and pointer points to 6, and now I set pointer to be the F-link, the pointer now points to the Sentinel node. So in fact, the stopping condition for a circular list involving a sentinel node is to stop when the pointer becomes equal to the sentinel.
Yeah. No.
Okay? So that's because this isn't a do until loop, this is a do while. So I do while the pointer is not equal to the sentinel. That's why this was one of the worst inventions in history, was the fact that the condition for exiting a loop is a negation of the condition you're waiting for, right? What the right way to have designed a loop was to, instead of had a while loop, would have been to have an until loop. Until pointer equals sentinel, execute the loop body. But the geniuses back in the 50s didn't design it that way because they were mathematicians, and mathematicians don't have a problem with negation. Only the rest of the world has a problem with negation. Okay? So they designed their loops so that you had to figure out what the condition for exiting was, and then you had to negate it. And that's why I negated the condition, because in fact, we keep executing until while the pointer is not equal to the sentinel. Okay. So lab 8, you will be implementing doubly linked lists. And the way you will know to stop your traversals is when the pointer becomes equal to the sentinel node. Okay, so questions about this so far? Okay. Now, let's say we want to insert into the middle of the list. So there's a bunch of operations that we are supporting with doubly linked lists that we weren't supporting with queues. So first of all, we're going to allow either push front or push back because lists are the most versatile. We're also going to allow pop front or pop back, so we can insert and remove either from the front or end of the list. But we're also going to allow insertion into the middle of the list. And it helps to be able to either insert before a node or after a node. So we're making the user give us the target node that we are inserting before or inserting after. So for example, if I have this doubly linked list, and D points here, then insert before is going to put the new item right there between 1 and 2, and insert after is going to put it right there between 2 and 3. Okay, but I need my target node to know. So again, I don't really like such, shall we say, terse variable names. I would have preferred something here like target, okay, to indicate where, or reference point, or something that's a little more informative. Okay, so in your own code, try to come up with more informative names, but this is what we have here. Okay, and now we're also introducing iterators. So begin is going to return a pointer to first node in the list. And end, this is very important, write this down, returns a pointer not to the last node in the list, but to the sentinel node. And that's how we know we've reached the end of the list. So in fact, when we're doing our iteration, we're not going to say pointer not equal to sentinel. We might like to, but the sentinel node is protected. Notice right here, the sentinel node is protected. So if you actually try to write a for statement that terminates when pointer is not equal to sentinel, the compiler will complain saying that sentinel is a protected variable. Won't work. However, end, the function end, gives us actually a pointer to the sentinel. So you can, in fact, really say pointer not equal end. Actually, it's going to be whatever your list is. And that's how you will terminate things. Okay. So, based on this, what do we think our begin should do? What should our begin return a pointer to? Okay, returns a pointer to what? Very good. So returns a pointer to sentinel B link or the last node. And I'll put in parentheses sentinel B link. Just like the first node in the list is, what's the first node in the list? How do you get to it? Sentinel and F-link gives you the first node in the list. And what do we think our end returns? Very good. So actually our end does the same thing that end does. It returns a pointer to the sentinel node. Now, we're only using one sentinel node in our list. So in each case, it returns a pointer to the same node. Okay, so those are the operations that we're implementing. Okay, so he doesn't give you the code for doing actual implementation because that's what you're supposed to do in Lab 8. So we're just going to talk about the implementation, walk you through it. Okay, so the hard cases, push front, push back, push front and push back are just inserting at the front and the back. Okay? We're actually not going to worry about that for a moment, and we'll see why. We're actually going to focus on insert before. So let's say we want to insert before this particular node. And we'll just say we have a pointer, I'll call it target. And we'll say target points right here. So if we're inserting before it, clearly we have to create a new node. For now. Okay, so we're going to have to create a, I'm going to get rid of this because I need some space. So I'm going to create a new node for now. A new node points to it. Okay, so clearly I have to assign now to S. Okay, I'm going to have to make new node. Let's see, don't have enough space here, so I need to make new node flink point to what? To target, because it's going before target. So we need to make new node flink point to target. And we need to make, so I'll go over here now. We need to make new node flink, or I'm sorry, blink, point to what? Needs to point to what? Targets what? What's going to be the node before now? It's going to be give, right? Now, to make your life simple and to make the life simple of someone who's looking at your code, I suggest that you, just like the book did, create two more pointers, one that points to the next node and one that points to the previous node. So I think your life will be a lot easier in that case, because give is really then previous node. But wait, there's more. That's not enough. That will certainly link new node into the list so that it points to target as its forward link and give as its backward link. But what do we also have to do to link it into the list? Make what? Very good. So, and which, specifically, which pointer in previous node needs to point to it? Very good. So we need to make flink point up here to new node. So we need to make previous node. I'm just going to say previous node must point to new node. I'll let you figure it out. How? And what must also point to new node? Target's blink. So we need to make target point. So those 5 operations, plus you need to remember to increment size. Okay, now let's look at those special cases, because I chose the middle of the list. Okay, so what happens is, okay, if I erase this, you got it all down? Got it? Yep, okay. So what happens if this is my target and I'm inserting before? Whoops, that's no good. Can't insert. Actually, I can. So let's say that this is, I'm inserting before the target. And the target happens to be the sentinel node. Is there just any problem with this? There's no problem. Okay, I'll take my questions in a moment. Let me get through this. So if the target points to the sentinel node, there's no problem, because it means that the previous node, I'm sorry, the next node will be here. And actually, I never need it. Okay. Going back to those previous notes, next node was never needed. Okay, I was thinking ahead to the delete procedure. If you're looking at the notes later and you're wondering why did Dr. van der Zanden have a next node pointer, he shouldn't have. There was no reason for a next node pointer. I never used it. Okay? So in fact, there is no reason for next node, only for previous node. Okay, so if target points to the Sentinel node, what I'm really doing is inserting before the Sentinel node right here. So its B-link gets that, and the F-link for this thing will be this. All I'm really doing is actually inserting at the end of the list. But that's sweet. I didn't have to do anything special. I just did an insert before the target. I'm sorry, insert before the Sentinel node, which is really push back. Push back adds to the end of the list. So actually, if I've implemented insert before, I can easily implement insert back by simply inserting before the Sentinel node. Very nice. Okay, well, what if target happens to be the first item in the list? Is that going to give us any issues? Well, no, it's not, because now previous node is simply the Sentinel node, and the item will come in here between the Sentinel node and the first node in the list. In fact, that's really sweet because we just inserted a new item at the front of the list. We did a push front. So in fact, push front is really just an insert before the first item in the list. And it was easy. We didn't have to worry about a boundary case because the first item in the list, it pointed back to the Sentinel node. It was real easy to insert an item before the first item in the list. No special case. Okay? So in fact, there is no special cases here. That's great. Push front and push back are actually trivial. In fact, insert after is also trivial. Okay, let's say that I want to insert after him. So if I want to insert after now, and I have a pointer to him, that's really equivalent to insert before, now, and what? I want to insert before 6, so what? How do I get 6? Target what? Flink. So in fact, once I have insert before, it is super easy to implement 3 of the other inserts. It's trivial. Okay? So that is how you do insert. I think you should be able to figure out how to do delete. I will briefly cover it next Thursday, but if you get started on the lab early, I don't think it's going to be a huge issue for you to figure out how to do the delete operation for a doubly linked list. Okay? Remember, exam on Tuesday.